Okay, so it looks like most folk are back now, so let's crack on with this afternoon's talks. The first one is really just a rather random collection of bits of useful advice for practical development and use of OpenMP. So these kind of the things that you don't see in necessarily in other places, or just useful stuff that I've picked up over the years and through teaching students and seeing the kind of mistakes, seeing the kind of common mistakes or problems that people encounter. Okay, so in no particular order. So start off with directives. So depending on which compiler you're using, if you mistype the Sentinel, that may not raise an error message. Say some C compilers are better and they will pick this one up. They will say, unrecognized pragma or something like that. But for Fortran, because if anything that starts with an exclamation mark is just a comment, it will just get ignored. So you do need to be careful. It's extra nasty if it's. I mean, so most of the time, if you mistype OMP parallel do, then if you mistype the Sentinel, you just won't get any parallelism, which is disappointing but not dangerous. But on the other hand, if it's atomic, for example, then and that just gets ignored, then you could end up with an unintended race condition. If you know that you're prone to common typos, then it's maybe just worth writing a little script that searches your code for them. So OpenMP, the way that OpenMP directives are designed is to help you be able to write code that functions both as a parallel OpenMP code and as plain old sequential C, Fortran, C++. Right? So that's fine, but if you have things like runtime library routines in there as well, then you need to be able to take care of those if you're not compiling with OpenMP. So you can do portable pre-processing, because the macro _OpenMP is defined if the code has been compiled with the OpenMP switch on the compiler. So you can use that as a portable way to conditionally compile code, so that it always works with or without OpenMP enabled. I say the OpenMP standards, or at least the old ones, used to have a dummy library in the back of the standard, but probably nobody really wants to go that way these days. Conditional compilation is generally much more convenient. Okay, talk a bit more about this in the next session and focus more on performance, but it's quite common for programmers not really to have a grasp of how much overhead there is in a parallel region. Okay, I say it does depend on the compiler, or more strictly the runtime library. It depends on what hardware you're running on. It depends on the number of threads that are executing. But very roughly, finger in the air speaking, the overhead of executing a parallel region is in the sort of tens of microseconds range, right? Which is small, but not nothing when you've got processors operating at with a clock frequency as several gigahertz. So it's, you know, several tens of thousands. It's like tens of thousands of clock cycles. So you just need to be aware that the sequential execution time of a section of code has to be at least this, and preferably several times that overhead, in order to make it worthwhile parallelizing. Otherwise, you're just going to incur a load of additional overheads. One problem you can come across in real applications is that a parallel reader or a block of code may take very different amounts of time to execute on different instances. Okay? You might execute the same piece of code in loop lots and lots of times, but only sometimes is it long enough to be worth parallelizing. So you can use, one way of getting around this is you can use the if clause to decide at runtime whether to go parallel or not. So you can say OMP parallel if then some condition, and if the condition evaluates to false, then the parallel region will just be executed on one thread. Doesn't completely get rid of all of the overhead. You still have at least a call into the runtime library still present, but the overhead on one thread is typically much smaller, so much less than a microsecond. So the overhead for one thread is sort of a couple of orders of magnitude smaller. So that helps quite a lot. So you can make a runtime choice depending on the value of variables in your code, whether to execute in parallel or not. Okay. Next one up is what can you? It's basically, this is a question of what assumptions you're allowed to make about the way that loops are scheduled. So example here would be, so I have a parallel region and I have two parallel loops inside it, and the loops have the same bounds, same number of iterations. And the first loop writes values into array A, and the second loop reads them. So there's I mean, this is just sketchy code here, so sorry if there's a missing semicolon that upsets anybody, but this is kind of just sketch code anyway. So the question is, do I need the barrier synchronization at the end of the first loop here? So can I guarantee that the thread that executes iteration I for this loop is the same thread that executes iteration I for that loop? And the answer is yes, provided the number of iterations in the loops is the same, and the schedules are the same, and they must be static, but they could be static with a chunk size. In that case, it is safe to use the no wait clause to get rid of the barrier on this loop, because you then are really guaranteed that the same thread will do the same subset of iterations for both loops, so that you know that reading AI here is safe, because you know it's the same thread that wrote it previously, and you don't have to wait for the other threads to complete their iterations of the first loop. So this is not really an important point, but it's just useful to know, I think. Actually, technically speaking, the default schedule for loops with no schedule clause is not actually static. It's implementation defined, but all the implementations do static, as far as I know. Okay. I think it's probably in practice it's okay to assume that you do get static without a schedule clause. But so for the previous case, it's probably better to specify it. Okay? And also you should note that schedule static doesn't actually completely specify the distribution of loop iterations. It doesn't specify exactly how you deal with any remainder. How, if the number of iterations doesn't divide exactly by the number of threads, it doesn't say how the remaining iterations at the end get dealt with. So I'm saying normally that's absolutely fine, but it's just you don't write code that relies on a iterations to threads. So while we're on the subject of loop scheduling, so if we have unbalanced loops and we want to use a static or dynamic schedule and specify a chunk size to try and get the load balancing right, that can be quite tricky because the optimal chunk size can depend quite strongly on the number of threads. So it's trying to choose a fixed chunk size that's going to give you good load balance or good results across a wide range of thread numbers can be quite difficult. So actually, it's actually more robust. Instead of tuning the chunk size directly, what you tune is the number of chunks per thread, and then derive. Then, if you know the number of threads, then you can derive the chunk size from that. The chunk size expression in the schedule clause doesn't have to be a compile time constant. It can be a variable expression. Next one is about single and master. So we've got actually these two ways of, inside a parallel region, executing a block of code on one thread only. And the others skip over it. So which should you use? Well, master has, at least in principle and in practice as well, actually, it has lower overhead. It's just a test, okay, on the thread ID, whereas single requires some synchronization because the threads have to agree on who got there first. Okay, the single will be executed by whichever thread gets there first, and they have to synchronize somehow so that they can agree on that safely. But beware that there's this asymmetry between these two. Okay, master doesn't have an implicit barrier at the end, whereas single does. So in both cases, you can change the behavior if you like. You can add an explicit barrier directive after the master if you need one, or conversely, with single, you can use single no wait to get rid of the implicit barrier. But there is this asymmetry there. On the other hand, if you have some reason for expecting some threads to arrive at this block of code before others, then it's probably worth using single, so that really the first thread to reach this block executes it, and so it gets done as soon as possible, rather than necessarily waiting for thread 0 to get there. Data sharing attributes. Yeah, common source of bugs is forgetting that private variables are uninitialized on entry to parallel regions. That's quite a common one. So clearly, you can use first private to initialize private variables, but it's more likely to be an error. So use cases for first private are surprisingly rare. Okay, so I'm not talking about tasks here. So first private for tasks is as we've seen this morning, is clearly vital in many cases. But first private for parallel regions or parallel loops is actually pretty unusual to require it. Okay, I'll make this point again, just to remember that the default behavior for parallel regions and work sharing constructs is shared. Okay, it's just relying on that is just very dangerous. It's very easy to accidentally share variables, and so you know, it's possible that this is possibly the worst design decision that OpenMP ever made. Okay, I really think it was a serious mistake, and it's probably caused more bugs and more people spending hours and hours debugging code than anything else. So I would say, you know, I know it involves some extra typing, but in the long run, it's always better to always use default none. There's this kind of strange effect that I've noticed with people writing OpenMP, is that it's what I call variable blindness. Okay, if you get somebody to read through a block of code and list all the variables that are used in it, they will often miss some. It's harder than you might. It's not such a trivial task as you might think. It's very easy to overlook things. So that's the reason that you know, I encourage you. So it's things like if a variable is only used in loop bounds, or only used in an if test, or only used as an argument, passed as an argument to routine, and doesn't appear on the sort of right, on the sort of normal right or left hand side of a statement, then it's easy to overlook those things, and that can have some disastrous consequences if you just allow everything to be shared by default. So, I mean, no, people don't really write code like this anymore, but you can end up with bugs like this. So, for example, here it's just like weird old-fashioned code without the declaration for J in here. So in this case, J would be accidentally shared. So that's just one example, which is a bit unrealistic maybe these days. Nobody really writes code like this anymore. Yeah, so in C, the parallel loop iterator, so I is okay, and the parallel loop iterator is always private by default. But J is just, as far as OpenMP is concerned here, J is just any old variable here. And it will be shared by default. And there's kind of an extra nastiness here with things like things like loop iterators or loop temporary variables, is that if you're lucky, you may always get the right result with sufficient compiler optimization because of the way that the compiler handles these things. So typically, if you have enough optimization on, then the value of the loop iterator, or indeed the value of loop temporary variables like temp here, is never actually stored in memory. Okay, so temp might be just stored in a register, So there's no need to ever, the compiler may decide that that's fine, and there's no need to ever load and store it into memory. And so you kind of get a private copy by default, or by accident, because every thread has its own copy of temp in a register. And same with loop iterators. If you know what the code actually looks like, if you look at the assembly code for an optimized loop, then you can find that what you see is that really what happens, you get a register initialized, it calculates the number of iterations, initializes a register with that, decrements it by 1 every time the loop, and then tests for when it's 0. So again, the value of the loop iterator is never actually stored in memory. And that's true even if it's used as a, for example, if it's used as an array index, that the array indexes will just be translated into address increments. Yeah, so you will never see, if with enough compiler optimization here, this might run correctly, and you'll never pick it up in a bug just by regular testing. And then suddenly one day you give the code to somebody else, or you change compiler, or you don't turn compiler optimization on, and then suddenly you have a bug. Okay, so the question is, are I and J here private? So yeah, I is private because it's the loop iterator for the parallel loop, but J is shared by default here because it's not declared inside the loop. So in this case, J would need to be declared somewhere outside the loop, and therefore it would be shared by default. But it's not just loop iterators that are the problem here. It's just easy to overlook potential race conditions, and yeah. If you declare it inside, if you use for int j equals, that's fine, because then the declaration is inside the parallel region, which means that every thread gets its own private copy by default. So that's fine, and that's how most people write loops in C these days. Anyway, I say it's this remark doesn't just apply to loop iterators. There are other cases where it's easy to miss things, and you might still get lucky because of the compiler optimization, if it does kind of accidental privatization for you. Okay, so this is a slightly nasty thing in OpenMP, which is to do with what happens when you make private copies of global variables. Okay, so I have some variable here, foo, which is declared at file scope, so it's a global variable. And then I have a parallel region and declare foo as in a private clause, so that I have private copies for the per thread for the duration of the parallel region. So that's fine. Okay, and then so the question is, what happens if there's a function call inside the parallel region, and the function here accesses the global variable directly, okay, via an extern statement. And the problem is that, what does this foo refer to? Is this foo the original storage in the global variable, or does this foo refer to the private copy? And the answer is it could be either. So if that makes a difference, then this is a problem. Okay, so yeah, you've no idea whether that's going to be the original storage or the private copy. And so this basically, this pattern is unsafe and unusable. It may vary between compilers. The real problem here is that is the ability of the compiler to do function inlining. So if the compiler decides to optimize this code by replacing the call to some func with just a copy of the code that's inside it directly, then the resolution to the global variable doesn't work anymore. So yeah, that's really the reason why this ambiguity exists. So if you really want the private copy, you would need to pass a pointer to it through the argument list, or you could use thread private. So there's this thread private mechanism for making private copies of global variables. Okay, so this one's really for Fortran programmers, and particularly if you're unlucky enough to be faced with some old-fashioned style Fortran. So it was quite common, at least at one time, to see code that looked like this. Okay, so you'd have loops, and then with huge, big, long bodies. Sort of a couple hundred lines of code referencing hundreds of variables inside the loop. So we have this real headache if you want to try and parallelize that loop. You've got to figure out whether all those variables that are used inside it should be private or shared or reduction. And that's tedious and error prone, and because if you get it wrong, you could get race conditions. Then testing it's difficult. So what do you do? Okay, in this case, it's probably a reasonable idea to refactor your code so that you put all the code in the body of the loop inside a function call, inside a subroutine call. And then anything that's temporary for inside the loop, you can declare that locally inside the subroutine, and then pass everything else through the argument list. So that's much easier to test for the correctness, but essentially you're making the same. You're doing a lot of the work. So this identifying temporary variables which can be declared inside is essentially the same process as identifying private variables, but it's much easier to test because you're just doing sequential refactoring. And then so hopefully you've the argument list here is a lot shorter than the total number of variables, and you've already you've already had to kind of list them and think about them, and then you can figure out how to parallelize it. As I say, so it's less of a problem for C or C++. You just wouldn't see typical code like that. But also you've got this ability to declare the temporaries inside the scope of the loop body and have them privatized automatically. Okay, yeah, this is a nasty potential source of bugs. So sometimes we want to have a parallel loop inside, so a work sharing loop directive inside a parallel region, and we want a reduction clause on the loop rather than on the parallel region, because we need the result of the reduction later on in the parallel region somewhere. Okay, so it's not it's not sufficient to wait, or it's not going to work to wait to the end of the parallel region to do the reduction, because we need the result inside the parallel region somewhere. So then think, okay, so need to initialize the value of sum somewhere. So let's do it just before the loop. That's probably where it was in the original code, and then make summer reduction on the loop. This actually has, well, it has more than one race condition. Okay, there's a relatively harmless race condition, but nevertheless a problematic one, is that all threads are executing. This is a parallel. This is just a bare parallel region. So all threads are executing sum equals 0. It's also a race because there is an implicit write to sum that happens at the end of the loop to form the reduction. And there is nothing that is not synchronized against this initialization here. Okay, so what can potentially happen is that one thread sets sum equal to 0 and then goes through, does all its loop iterations, adds its private copy of sum into the original value, and then sometime later some other thread comes along and sets it back to 0 again. So this is actually not safe. There is a race here. Again, you might get lucky. Some implementations of the reduction might be safe and others may not be, but you can't guarantee it. So the right thing to do here would be to, well, this is a simple case where you could move sum out, the sum equals 0 outside the parallel region. But you can't always do that, because if there's a sequential loop inside here, you might need to set sum back to 0 every time. So you might that might not be a possible solution. In which case you need to enclose sum equals 0 in a single or master followed by a barrier would work here. So that's a slightly nasty one to be aware of. So Vlad asking, are there any magic parallelizers on the market? Yes, people have produced automatic parallelization tools. They tend to work fine on trivial toy examples. As soon as you get real code especially with, as soon as you get function calls inside your parallel regions, then they tend to just give up. That's pretty hard for them to deal with. What there is, which is probably which are more useful, and so I think I'm probably going to mention it later, is tools for doing race condition detection. So there are tools that will you can run your code and it will run it'll do instrumentation on your code and then post analyze it for possible race conditions. So those tools really are useful. So you can check whether your code contains any race conditions. So they work in a completely different way to normal debuggers are no use for race conditions. Nor are your standard unit testing procedures are not may well not pick up race conditions either. So these tools there are tools for doing that race condition detection, which definitely are useful. So what you find with the sort of the automatic parallelizers as well is that what they will tend to do is they will always parallelize your innermost loops. So typically, Okay, so they'll do a good job of parallelizing your innermost loops, but then you find that you have this problem where your loops are too your inner loops are too short to be worth parallelizing, and you just end up with more overhead than benefit from parallelization. Okay. Oh, this is going back to the question we had this morning about does compiling with the OpenMP flag, does compiling sequential code with the OpenMP flag change anything? Okay. So yeah. So there's a couple of reasons, a couple of things can happen here. What you might do, the first thing you might ever do with your code is, okay, I'm going to use OpenMP, but let's just add the OpenMP flag to the compilation and see what happens. And then suddenly your code breaks. Okay, there's a couple of things that could have gone wrong here. One is you might have a bug, which is assuming that the contents of a local variable are preserved between function calls. So you're basically missing a save in Fortran or static in C or C++. So what's going on here is that if you compile with OpenMP, then you are forcing all local variables to be stack allocated and not heap allocated. So in general, the compiler has a choice. If it's just sequential code, the compiler has a choice as to whether it does stack or heap allocation. But compiling with OpenMP forces stack allocation for all local variables so that it can correctly implement the default behavior, which is local variables are private to threads. Because the way it does that is by allocating them on the thread stacks. So every thread has its own stack. So by forcing stack allocation means that's how it does the privatization of local variables. The other thing this can do is increase the amount of stack space that you need and can cause you to have stack overflow. Okay, in which case you normally get a nasty segfault type death. So you definitely need to, you definitely need to use save or static correctly. But then if you do, those things are then shared by default, which might cause you some problems. Okay. You can then declare them, if you need a thread private copy, you might need to make them thread private. One fairly common pattern that relies on using save or static is first time through code. Okay. So this is, I have a block of code at the beginning of my function, and I want it only to be executed once the first time the function is called. So I'll execute it and then set a flag, which means that block's not going to be executed on subsequent calls. So if you have that kind of pattern, then you might have to think about what you're going to do about that. If the first call is going to come from inside a parallel region, then what are you going to do? Right? You have to somehow agree as to which thread's going to execute it, or you might have to do some more complicated refactoring to get around that kind of pattern. So if you do have a stack size problem, so if you do have large private data structures, it's certainly possible to run out of stack space. And the control of this is slightly awkward. The size of the thread stack is, for every thread apart from the master thread, is controlled by an OpenMP environment variable called OMP stack size. So you can set that before you run the program, and that sets the stack size for everything apart from the master thread. but you still have to control the size of the master thread stack in the same way as you would for a sequential program. So that could be a compiler switch, or it could be a Unix command like ulimit to set the stack size for subsequently spawned processes. And the reason this is messy is that for the master thread, there's no way OpenMP control that, because it's the stack is set. The stack for the process is set by the operating system on process creation, and by the time, even if OpenMP library is invoked before you start executing any actual code, it's too late for it to set the stack size. It's not able to change what the operating system set. So you have to do. So typically, you may well need to do both these mechanisms to set all the thread stacks big enough. Okay, what next? Critical and atomic. Yeah, just be careful that critical and atomic don't mutually exclude. So you can't protect updates to shared variables in one place with atomic and in another place with critical if there's any possibility that they might happen at the same time. If you have large private data, is MPI a better solution? Maybe. Okay. Yes. There's all sorts of considerations there. There's no problem with having large amounts of private data in OpenMP, provided you allocate sufficient stack space. It's just that the default might not be big enough. Yeah, it depends on how big a stack you have, but I mean, it's certainly under Linux, then it's no problem, right? You can set it as big as you like, and you're going to be limited by the on a typical cluster, you're going to be limited by the amount of available physical memory rather than any limit on the stack size. So most HPC systems, you can have your stacks as big as you like, and you're going to run out of physical memory first. Okay, next one is allocating storage based on the number of threads. Sometimes you want to allocate some memory. So for an array, for example, whose size is determined by the number of threads. Okay, so you want an array of the size of the number of threads, or some data structure of the size of the number of threads. Okay, but how do you know how many threads the next parallel region is going to use in a portable way? Because you don't really want to have to read the environment variable, and also that the value in the environment variable might have been overwritten with a call to OMP set num threads, for example. So what you can do is you can call a different function. Okay, so you can't call OMP get num threads outside of a parallel region, because that's going to return you 1. Okay, if you call OMP get num threads out in the sequential part of the program, that just returns you 1. That doesn't tell you what you want to know. But there's this other function called OMP get max threads, okay, which returns the value that you want. Okay, so it's the way this works in OpenMP is that there are these there's some internal state in the runtime called internal control variables, or ICVs. And in this case, every thread has an internal control variable called nthreadsvar. And that's basically the number of threads it will use if encounters a subsequent parallel construct. Okay? So you're at least guaranteed that the number of threads used for the next parallel region will not be larger than that value, unless you use an explicit num threads clause on the parallel region. And so that allows you to say, okay, how many, it gives me something that's at least as big as the number of threads that will be used for the next parallel region, so I can declare so I can allocate my data based on the value of that. Okay, so it's kind of it's a bit unfortunate. These internal control variables were a later addition to the specification. So you'd really like, so this is the getter and setter terminology doesn't quite work here. Okay, so OMP set num threads does indeed reset the value of the end threads for our internal control variable, but OMP get num threads does not return that value. And OMP get max threads is the actual getter. So Lorenzo says it certainly does this. Okay, so you actually run a parallel region and work out how many threads there you actually got. Yeah, that's okay. Yeah. It's just worth, I guess it's just worth pointing out my next point here, really, which is that the implementation is always has a get out of delivering you fewer threads than what you asked for. Okay, so if your code really does depend on there being a certain number of threads, there are parallel algorithms that you can write where it doesn't make any, it won't work on one thread. Right? You need at least 2 threads for it to work correctly. Then you need to call OMP get num threads when you're inside the parallel region and actually check. So if you want to squeeze the most performance out of your OpenMP code, there are some environment variables that you should set to help and not rely on the defaults always. So defaults are implementation dependent. First one is OMP wait policy. Set that to active. It's actually just a hint. So what the runtime really does with that is, again, implementation dependent. But what this does is encourages idle threads to spin rather than go to sleep. So your idle threads will consume CPU cycles, but as long as you're okay with that, it's then faster to reactivate threads which are, say, waiting outside a parallel region. It's faster to reactivate them if they're spinning than if they're sleeping. Next one is kind of related to the previous slide. Set OMP dynamic equals false. So again, it's a bad piece of terminology choice. OMP dynamic has nothing to do with dynamic loop scheduling. OMP dynamic says is basically, again, it's a hint which says if it's true, then you're basically asking the runtime to match the number of threads to the current resources on the system. So the runtime may have a look at the load on the system and then choose how many threads it's going to give you. So again, if you probably don't want that to happen. If you don't want that to happen, then you should set OMP dynamic equals false to try and encourage the runtime to actually give you as many threads as what you actually asked for. And the last one is OMP proc bind. Okay, so this is, if you set OMP proc bind equals true, then you will bind you'll have your threads bound to cores and prevent them from migrating between cores while the program's running. So if you care about performance, that's probably a good idea. If you're operating under a batch system, then you probably don't need to do that. Depends on how the batch system's been set up. But mostly you'll find that batch systems will do the thread binding for you, and you don't need to care about this one. Okay, yeah, so we kind of mentioned this a bit earlier, so debugging tools. So, your traditional debuggers tools, HPC debugging tools do have support for OpenMP, which is fine, but they're not much help. Traditional debugging tools are not much help for tracking down race conditions. Because even if you know you've got a race condition because you're getting wrong and unrepeatable answers, then what can happen is that the running under the debugger changes the timing of events on different threads. So it's not uncommon to find that you run your code normally, you see the race problem, you run it under the debugger and the race condition goes away. So I mentioned these race detection tools that work in a different way. So what they're doing is basically capturing a record of all the memory accesses that happened during the run, and then analyzing that data for races which might have occurred. So it's things like Intel Inspector and Thread Sanitizer are definitely, if you're doing serious OpenMP development, I definitely encourage you to get familiar with one of these tools to check for race conditions. They do have they're not completely wonderful in the sense that they can produce false positives. You will sometimes see it throwing up race conditions where the race has come from some harmless race inside a library somewhere. Okay, so you have to recognize that that's what's happening and that it's not a problem with your code necessarily. And they do add, running under one of these tools does increase the runtime a lot and can produce very large output files. So you typically need to pick a small problem size or a short run. But the saving grace is there that for most applications, the presence or absence of race conditions doesn't depend on the size of your input data. So you could conceivably have exceptions to that, but it's pretty unusual. So normally, just running the code on a small problem will still pick up the race conditions, because you're not relying on the races of actually happening. You're basically analyzing the memory access and synchronization patterns to see whether races could have happened. They don't necessarily actually need to have occurred in that particular run. Okay. Yeah, timers. So be careful, particularly if you inherit code that already has some timing routines in them. Have a look and see what it's actually using. Okay, so OpenMP's built-in timer is a useful one. Okay, it does measure wall clock time. It also returns a double precision value in seconds, which is quite nice. There's other things like the Linux clock routine, for example, which doesn't measure wall clock time. What it actually measures is the CPU time accumulated across all the threads in your process. So if you use that and then wonder why you're not seeing any speed up, well, you're not going to, okay? Because your accumulated CPU time is probably only ever going to increase with more threads. So yeah, just be careful. I say, especially if you inherit other people's code that already has timing in them. Go and have a poke around in the code and see actually what timing routines they're using, and make sure that makes sense. Okay, done for that one. Any other questions? Okay, so I need a drink, so I will take a 2-minute break and then come back for the next one. Okay, so question from Vlad. What's my view about Valgrind for debugging OpenMP? So yeah, Valgrind does have a race detection. Well, there is a race detection tool as part of Valgrind suite. I don't have a lot of experience of using it, to be fair. But yes, it does contain a tool for race detection, which is useful. I have more experience with the Intel one, to be honest. But I think they're essentially doing the same thing. Yeah, there's a couple of tools. So it's Hellgrind or DRD. It's parts of the Valgrind suite of tools that you might want to try out. Okay. Right. Performance. Here we go. Okay. So I guess most of you have some experience of developing OpenMP, so maybe you've been here. Okay. So I wrote my OpenMP program and I checked it gave the right answers, and then I ran some timing tests, and well, the speed up was a bit disappointing. Now what do I do? Okay. Where did my performance go? Well, this might be a slightly unconventional way of looking at performance issues, but I find it helpful. So I'm going to share it with you. The way I like to think about it is that the time disappeared into some overhead somewhere. Okay, so there's various different sources of possible overhead in your parallel program that prevent you from getting perfect speed up. Okay, so and there are a lot of them, but you can classify them into basically 6 different categories. Well, 6.5. Okay, but the 6 main there. So for OpenMP programs, there are really 6 main categories of problems that can go wrong. So we'll talk through each of those in turn. We've got sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. And the 6.5 is to do with compiler optimization, which I'll mention at the end. Okay, so let's have a look at each of those. Okay. First one is simple. Okay, so sequential code. So in OpenMP, so code outside parallel regions or inside master or single directives, it's essentially sequential code, and just the time spent in sequential code is going to limit your performance. So it's just simple Amber's law type arguments. Okay, so if the code that accounts for 20% of my original execution time is not parallelized, then there's no way you're ever going to get more than a 5 times speed up. So if that's the case, you just simply need to, basically your job's not done yet. There are still parts of the code that are consuming significant execution time and need to be parallelized. So that's at least conceptually okay. Conceptually straightforward. Practically, okay, of course that might be difficult. Okay, those bits of code might not parallelize easily or at all. But at least then you know what's the problem. So the second one is idle threads. Okay, so this is situations, for example, where some threads finish a piece of computation before others, and have to wait for others to catch up. So in OpenMP, the most common situation is we end up with threads sitting idle in a barrier at the end of a parallel loop or a parallel region. Okay, so this is supposed to be a kind of generic activity timeline type thing. Okay, so basically showing 4 threads where the blue stuff is used for computation. And so time goes from left to right, so from the start of the parallel region to the end of the parallel region. And the 3rd thread here takes longer to execute its work, which means that the other threads are basically sitting there idle, doing nothing in the barrier at the end of the parallel region, waiting for the 3rd thread to get there. Okay, so basically just simple load balancing problems. Can you identify add threads and tools? Yes. Okay. So there are. I'll mention at the end about some profiling tools, which will do this. Okay. As I say, as we'll go along as well. So idle threads is one of the sources of overhead that tools are actually quite good at picking up. Whereas they really struggle with some of the other ones. So I'll kind of discuss that a bit later on as well. Yeah. Okay, so what can we do to avoid load imbalance? Well, clearly, if it's a parallel loop, then you can experiment with the different schedule kinds and chunk sizes. And this convenient mechanism of using schedule runtime to avoid recompilation. Okay, so you can specify schedule runtime on the loop, and then set the actual value of the schedule and the chunk size in an environment variable. So it makes it easy to do experiments without recompiling. Okay, yeah, and as we talked already about this morning, more irregular computations using tasks can be helpful in situations where you can't just simply use loop schedule kinds. Just a word of warning, it's not necessarily always safe to assume that 2 threads doing the same computation will always take the same amount of time to do it. It's a reasonable assumption, but it's not always the case. Why not? It's because the time taken for different threads to load and store their data may be different depending on things like if or where that data is currently cached. So the state of the memory, the way the data is currently laid out or stored in the memory system may affect the execution time. So some threads may you might be doing exactly the same number of floating point operations, executing exactly the same code, but they don't necessarily take the same amount of time because the time taken for threads can experience different numbers of cache misses, for example, and that's a potential source of load imbalance. You can get idle threads in other places. So, for example, waiting to access a critical section. So in OpenMP, critical regions, atomics, lock routines can all cause idle time. So, for example, in this time, if the green stripy block is a critical section, which means that only 1 thread at a time is allowed to executing it, then the first thread that arrives, say the thread this one, will go ahead and execute it, and then the others have to wait their turn to get through to acquire the lock or get through the critical section. So you can also have idle time there as well. What can you do about it? Well, you can try and minimize the time spent in the critical section. You can try to really work hard to optimize the code that's in the critical section, remove anything that's not in there that's not needed, and work to try and make it execute as fast as possible. So OpenMP critical regions are really just a syntactic convenience for a global lock. As I say, you can use if you have more than one thing, data structure or concept to lock, then you can use critical directives with different names to lock different things. So you get more than one lock. In general, you should always use atomics if possible, in preference to the critical sections. And obviously, atomics have a limited applicability. It's really just updates, single statement updates to basic types. But if you can use them, they do permit them. They are faster, have lower overhead, and they also using atomics also allow you're protecting the actual memory location on the left-hand side here, rather than the block of code. So atomic allows, for example, concurrent updates to different array elements. So if the thing on the left-hand side that you're updating is an element of an array, then if you have atomic, then it allows different threads to update different array elements concurrently, whereas critical doesn't. Or you might end up using multiple locks. Okay, so situations where you have where an update is more complicated. An update to a shared object is more complicated. So you might end up with a lock per object or something like that. Okay, next one is synchronization. Okay, every time we synchronize threads, there's going to be some overhead, even if the threads are never idle. Okay, so even if all the threads arrive at the barrier at the same time, or even if threads are never waiting, threads are using a critical section, but they're never contending or waiting, there's still some overhead associated with actually executing that synchronization construct. Because at some level in the hardware, the threads have got to communicate somehow. So all synchronization actually comes down to memory accesses at some level in the hardware. A lot of OpenMP codes, OpenMP style encourages a lot of implicit barriers. So the end of every parallel region, the end of every parallel loop is a barrier. Okay, and barriers are quite expensive. Okay, so it obviously depends on the number of threads and the runtime and the hardware, but typically looking at thousands to tens of thousands of clock cycles for a barrier. And the other constructs like criticals and atomics and locks aren't free either. And nor is creating and executing a task. Okay, so that also requires some internal synchronization between threads. So what we can do, well, we can think about parallelizing at the outermost possible level to try and minimize the frequency of barriers. Most of the problems you see with the excessive synchronization in OpenMP code is probably down to two barriers. May not be trivial, might require you to do some reordering of loops, and that in turn might force you to reorder your array indices as well if you're unlucky. If it is genuinely safe to remove the barrier, then you can use no wait clauses on your loops. But again, you need to be careful. It's just very easy to accidentally introduce race conditions by removing barriers that are actually needed. Okay. And again, atomics are typically better than critical or locks if they're applicable. Okay, next possible cause is scheduling. So if we are creating computational tasks and then relying on the runtime to assign these to threads, then that incurs some overheads. That's not for free. Okay, so some of that might actually be internal synchronization in the runtime. Okay, so there's a little bit of ambiguity between this this category and the previous one, but nevertheless, okay. So this is really thinking about if we have loop schedules which are not static schedules, so dynamic or guided or auto schedules, and task constructs. Okay. So if you do something like this, if you have a very long loop where the loop body doesn't do very much, and you specify a schedule dynamic with a chunk size of 1, then you can easily get into an awful lot of overheads, because every single loop iteration requires it requires to be dynamically scheduled and some synchronization to be happening in the background somewhere. And as we talked about this morning, you need to get the granularity of tasks right. Okay, and that's also, I mean, that kind of applies to the loop schedules as well. That just means that just translates to you need to get the chunk size right. Okay, so you need to get the granularity right. If you have if your tasks are too big, then you might end up with idle threads. If you've got too many little tasks, then you'd end up with a lot of scheduling overheads. So typically you need to find the right compromise in between. Okay, any questions so far? Okay, so those ones are all fairly straight. Oh, Lorenzo, go for it.
Yeah, no, a quick question. So you said that every parallel region and every parallel loop has an intrinsic barrier. Is that correct?
Yes.
So if I open a parallel region, do some work where I create like a private variable for the threads and do something per thread, and then open a parallel loop, that means that I have 2 barriers.
Well, if the end of the parallel loop is followed immediately by the end of the parallel region, then the compiler might optimize one of those away for you.
Okay.
But that's a might rather than a definitely will. Okay.
All right. Good to know. Right. Thanks.
Yeah. So yeah, if you're, if the end of if the two barriers really do come one after the other, then you have some chance that the compiler spots that and optimizes one of them away. But as with all compiler optimization, there are cases where it won't work. Okay, anything else? Right, let's talk about the nasty stuff then. Okay, so next one up is communication. And the problem here is that in shared memory systems, the communication is kind of disguised. It really sort of shows up as increased memory access costs, because it takes longer, excuse me, it takes longer to access data that's in main memory or that's in another processor's cache than it does to get it from the local cache. And you have to remember, on modern hardware, memory access are expensive things, so talking order of 100 or 200 clock cycles for a main memory access, compared to a few clock cycles for a floating point operation, or it's like one or two clock cycles to get data from the level 1 cache. And so communication between processes or between cores takes place via the cache coherency mechanism in shared memory hardware. And the problem is that, in contrast to message passing, the communication is very fine-grained. Okay, it's down at the level of individual loads and stores, and it's also spread out throughout the program. okay, which makes it much harder to analyze or monitor. So either it's harder to visualize by looking at a program. Okay, so I look at an MPI program, I know immediately where the communication is taking place. Okay, I know that the only place that communication happens is if I make calls to the MPI library. Okay? If I look at a shared memory, if I look at an OpenMP program and say, okay, where's the communication between threads taking place? Well, actually, I don't know. Okay, there are lots of loads and stores in my program. Some of those might cause inter-thread communication, and some of them won't. But just examining the code doesn't readily tell you where the communication is happening. And the fine graininess also makes it harder for any tools to monitor it. So again, it's quite easy for MPI programs to be instrumented and by tools which record how many bytes were sent by every message, and when it was sent, when it arrived, how long it took to transit the network, all this kind of thing. So you can get tools to tell you that kind of stuff reasonably easily, but monitoring individual loads and stores is much more difficult without massively impacting the performance of and the behavior of the program. So that means it's actually quite tough to deal with. Okay, so cache coherency is complicated in detail, but I'm going to try and explain what happens roughly speaking, what happens in a single slide here. So remember that the way modern hardware is designed, basically every core has its own local caches of data on it. Cache hierarchies are quite complicated. The cores typically have level 1 and level 2 caches, and then there's often a shared level 3 cache between some subset of the cores, or all the cores, or something, depending on the hardware design. But anyway, what happens is that whenever a thread writes a data item, it will get an exclusive copy of the data in its local cache. Okay, so that will become the latest, the only and latest up-to-date copy of that data item. And any copy, when that write happens, any copies of that data item that happen to be in other caches at the moment, those will get invalidated in order to avoid other threads on other cores reading out-of-date values. Okay. So then, if those other threads running on other cores then try to read or write that data item, then they have to go to the cache they have to communicate with the cache that has the exclusive copy in order to get the most recent version. And this takes time because it requires moving data between one cache to another in the system. Okay, so that's a very high level, very highly simplified description of the way that the hardware is working. So the reality is a bunch more complicated, but at least if we have that kind of picture in mind, then that's fine. Okay, that's good enough. So think that every time a write happens, all the other copies get invalidated, and every subsequent access has to go and get the latest copy from the place where it was last written. So what does that mean for our OpenMP programs? Okay, well, data will be cached on the processes that are accessing it. So we have to reuse cached data as much as possible. Okay? So this is really just an extension of the of the normal locality concerns you have with optimizing sequential programs. We've just added this extra parallel dimension to it. So really what that means in practice is we need to write code with good data affinity. What does that mean? It means trying to ensure that the same thread accesses the same subset of program data as much as possible. And also, so for reasons we'll come on to, is try and make those subsets reasonably large contiguous chunks of data. Okay, so we don't want fine-grained interleaved accesses to memory from different threads, and I'll explain why in a minute. Okay, and this is also why it's important to prevent threads from migrating between cores while your code is running. Okay, because code is running on one core, it will get some of its working data stored in the local caches on that core. If that thread then migrates, if the operating system decides to move the thread and run it on a different core, then it has to wait for all its all that cache data is in the wrong place, and it will have to go and fetch it from where it was running previously. Okay, so here's sort of an example of where things can go wrong. And so, okay, just talk. There's a little bit of complexity here, so just talk through this example a bit carefully. Okay, so we've got two parallel loops here, and I want you to focus on the second one to begin with. Okay. So the second loop, so we've got a loop nest here, which reads values from this array, this two-dimensional array A here. Okay, but if we look carefully at the loop structure here, so the bounds for I are 0 and n, but the bounds for j are 0 and I. Okay, so this is a triangular loop nest. So if we want to parallelize the outer loop with a parallel for directive, that would not naturally be well balanced, because the larger the value of I, the more work there is in the j loop. So if we just think about this loop in isolation, then we might decide, well, it's not balanced, so let me choose a suitable schedule. Okay, so that might be, for example, I might choose a static schedule with a chunk size of 16, say. Maybe that turns out to be a sensible value. Now let's look back at the previous loop. Okay, so this is the previous place in the code where this array A had its values written. So this loop nest assigns values to Aij. But this loop isn't triangular, it's rectangular. So the j bounds here are 0 and n. So there's no reason. So this I loop is well balanced. So there's no a priori reason for load balance to do anything other than a static schedule. And then let's think about what's going to happen here in terms of the accesses to Aij. So the problem here is that for the most part, the thread that access for a given value of I and j, because of the different schedules, the thread that reads Aij here is not the same thread that wrote it in this loop. So provided that that A is not too huge and fits in some level of cache, then what this is typically going to mean is that these reads here will need to go to the remote cache on another core to retrieve the up-to-date value that was written by some other thread. Okay. So this is an example where the code does not have good data affinity because we're not accessing the same subset of data by the same thread. So a pattern like this is going to result in a lot of communication. So in a case like this, there is a fairly simple solution, or potentially fairly simple solution, and that would simply be to apply the same static 16 schedule to the first loop as well as the second, and then you would get the same. Then you would get the same access pattern, for example. So in reality, it may be more difficult to arrange that. Okay, so here's another example. Okay, so suppose we have so really this sketchy code here. Okay, suppose we have a parallel loop that reads some values in an array A, and then we have a sequential loop that writes some new values into A, and then we repeat the original loop again. Okay, so we repeat the loop that does the read. So what's going to happen here? So these read accesses will come from different threads. So we'll get copies of different bits of A spread across multiple caches. This loop that writes all of them, so that's going to invalidate all those copies, apart from thread 0, okay, apart from the ones that were on thread 0 here. All the other copies will get invalidated by these writes. Okay, so the latest copy of all of your array will end up in one cache here. And then these accesses here most of these accesses are going to be accesses to remote caches again, to retrieve the latest values. So what will you see here? Okay, so not only you will see, okay, probably this loop won't scale very well with increasing numbers of threads. Okay, this loop won't scale very well because of these extra memory access costs. What you might also observe, which is kind of really non-intuitive, is that this sequential loop will take longer if there are multiple threads executing these other loops. Okay, so your sequential loop may actually increase in time because of those additional costs of doing those cache invalidations. So that's kind of non-intuitive behavior. So you can really sometimes see that there are sequential bits of code that actually take longer to execute when you have multiple threads executing. Okay, so you might need to, for these reasons, you might end up parallelizing code which doesn't actually appear to take time in the sequential program. So again, solution is easy here. I mean, we could just parallelize this loop, or probably better, we could try and say combine two of these loops together. And that would improve the sequential cache locality as well. So if we were able to merge this loop into this one and parallelize that, that would be even better. Okay, so that's quite complicated to think about because it's not obvious. All the caching is happening transparently in the hardware, and it's not easy to inspect a program and figure out what's going on in terms of the cache behavior, and it's not easy to get tools to monitor it for you either. Okay, it gets worse. So NUMA effects. Okay, so if we have multi-socket systems, then the location of data in main memory becomes important. Okay, and so most HPC systems, most current HPC systems are multi-socket. They all, for some reason, because it's just the sweet spot in the hardware, the correct number of sockets in a node is 2. Okay, so that just seems to be the right design point for current hardware. Now, ARCHER2 is no exception. Okay, so every node in ARCHER2 has 2 sockets of AMD ROM. The AMD ROM is actually more complicated because each socket actually has 4 separate NUMA regions. So every set of 16 cores on ARCHER2 is a separate NUMA region. Okay, so basically, okay, this is important whenever you are running threads that expand. If your set of threads extends across more than one NUMA region in the hardware, then we need to worry. Okay, so OpenMP doesn't have any support for controlling where the data is actually placed. So the common default policy for the operating system, so particularly for Linux, is to place data on the on the memory that's close to the processor which first accessed it. Okay, so the first time a piece of data is accessed in the program, that's when the actual location in physical memory is determined, and the operating system will try to place the memory in the same NUMA region as where that access came from. So for sequential programs, great idea, no problem. For MPI programs, makes total sense. Okay? So because every MPI process is only ever going to access its own data, so having that local to having that instantiated in the same NUMA region in the hardware makes total sense. For OpenMP programs, this can be the worst possible thing that can happen, because provided that if we do all our data initialization in the master thread, so if we don't parallelize our data initialization, what's going to happen? It's all going to get allocated on one socket, because the first access to all of our data comes from the same thread running on the same core, and we get all our data accessed on allocated in the same socket or same NUMA region, and then having all your threads accessing the data, accessing that same socket or NUMA region, that becomes a bottleneck. What can we do? Well, what can we try to do? So depending on the operating system, there are some options to control the data placement. Okay, so for example, in Linux, you can use, there's a command called NUMActl, which allows you to change the placement policy for a program. And so for example, you can change it from first touch to round robin, which just means it's going to cycle as pages of data get accessed. They just get allocated in a cyclic fashion round all the NUMA regions. However, that might help a bit. On the other hand, we can actually make use of the first touch data policy to control the data placement indirectly by actually parallelizing our data initialization. So that might not seem worthwhile at all, because your initialization might take a completely insignificant amount of time compared with the runtime of the rest of your program. So why would you bother parallelizing it? Well, maybe because that determines where that data is going to be resident in memory. You typically don't have to get the distribution exactly right, and in fact, for some applications, it may not be obvious. There may not be an obviously right distribution. Okay, but at least some distribution is usually much better than none at all. Just want to really avoid this pathological case of having all your data in one NUMA region. And this is easy enough to do if our main data structures are, say, large multidimensional arrays. And then parallelizing their writing a parallel loop that just initializes the whole array, and that's easy. Okay. Other codes have much more complicated data structures, which are not, which might be allocated in small pieces and grown organically. So you might have tree or graph-like data structures which are not all allocated in one go. They're allocated in lots of small pieces, and parallelizing that might be a whole bunch more difficult. And just to remember is about the granularity of allocation here. Memory allocation is done in operating system pages. Okay, so well, how big are those? Depends on the operating system, but typically a few kilobytes in size. Some operating systems allow you to have an option to use much larger pages, so megabyte-sized pages, but that might not be terribly good for this, because if the granularity of your distribution gets very big, it can be difficult to distribute your data structures easily. Okay. Last but not least in this section is fault sharing. Okay. Well, I've described this as very, very evil. Actually, modern hardware is getting a bit better at mitigating some of these effects. They're still there. You can still observe them. Hardware designers have put a lot of effort in to try and make this less of a problem. What's going on here? Well, we talked about the cache coherency operations, this process of invalidating old copies in caches. The units of data on which all this happens is cache lines. So these are typically 64 or 128 bytes, but they're always bigger than a single word. Okay, so your single word of data depends on whether it's an integer or floating point or double precision, will be typically 4 or 8 bytes. Okay. So the problem is that if we have different threads writing to neighboring words in memory, so there's no actual sharing, there's no actual sharing of data or communication happening. So this different threads happen to be accessing words in memory that are next to each other. That may be sufficient to cause these cache invalidations to happen. And so it's still a problem, even if we just have one thread writing and others reading, because as long as at least one thread is writing, then these invalidations are still happening. So typically the worst cases happen where we have so the pattern where this happens is you have different threads repeatedly writing neighboring array elements. Okay, so if you're ever tempted to write code that says, okay, I've got some array and I'm going to index it with the thread number. Okay, so that guarantees you this kind of behavior, because different threads are going to be writing neighboring elements in the array which lie next to each other in memory. Or you can also run into problems with patterns like this. Okay, so suppose I have this unbalanced loop nest again. Okay, and say decide that okay, this is unbalanced because the j upper bound on j is I. Yeah. Okay, and so okay, so choose a static schedule with a small chunk size. Okay, but because the parallel loop, the I loop here, is indexing an array, that also means if I choose a chunk size of 1, that means that neighboring values of I, and therefore neighboring elements of B, are being written to by different threads. So in this case, what will typically happen is you'll see that as you make the chunks, if you make the chunk size a bit bigger, then the performance will actually get better. So it means that this is a case where, although chunk size of 1 in principle would give you the best load balance, it can actually cause these false sharing overheads. So you might find that a larger chunk size is actually better in this case. Whew, okay. On to the last one here. Okay. Hardware resource contention. Yeah. Okay. So designing shared memory hardware is, there's some cost versus performance trade-offs going on in the hardware here. And what that means is basically there are some shared resources. If all cores try to access them at the same time, aren't going to scale. Or you can look at it the other way around. An application, a single-threaded application running on one core can access more than its fair share of resources. Okay, so more than one core's worth of resources. And in particular, what resources are we talking about here? Well, in cores and OpenMP threads, particular for memory bandwidth, okay, so access to main memory, and also to if there are also bandwidth to shared levels of caches. So typically your level 3 cache will also be shared between some number of cores. You can also contend for level 3 bandwidth. You can, if there are shared caches, you can contend for cache capacity. Okay, so for these shared caches, if we have one thread running, then it probably gets access to, it probably is able to use the whole cache. Whereas if we have multiple threads running, then they have to share it. You can also, if you're using simultaneous multi-threading, so hyper-threading, virtual cores, whichever terminology you favor for this, okay, so where you're using the hardware support to run more than one thread per core, then you can end up contending for functional units, so the floating point units in particular. So what does this mean? Well, particularly for codes which are very memory bandwidth hungry, they are just not going to scale linearly on most shared memory hardware. And that's actually typically quite difficult to do anything about. And it can often be the limiting factor in how well your OpenMP code scales. You can try to reduce the bandwidth demands by improving locality and therefore improving the read caches, which is also going to benefit your sequential performance as well, most likely. But it can be difficult to do anything about. So, okay, don't want to plaster you with too much data, but I think this is a really interesting case. Okay, so this is for the AMD Rome processor. So this is what's in ARCHER2, and I am just looking at what happens inside one NUMA region. Okay, so just up to 16 cores. So we have so there's no NUMA effects going on here. We're just looking at the contention for the memory bandwidth inside one NUMA region. So each core has its own level 1 and level 2 caches, and then every set of 4 cores has a shared 16 megabyte L3 cache. Okay. So what did was, okay, this was using Cray compiler, so it does a good job of optimizing code. So just run this simple parallel loop here. Okay, so the fact that there's a scalar reduction here doesn't matter. Okay, it just means that this is just pure memory read bandwidth. Okay, so what we're looking at here is just multiple threads all accessing part of a large array. So I'm going to, what I did was run this loop and run it enough times such that any initial cache misses are negligible. Okay, so get myself into a state where if this array, if parts of this array fit in any of the caches, then it's going to be there and stay there. And then basically, okay, measure the speed up that I get for this loop for different values of n. Okay, so it's different sizes of the array and different numbers of threads. Okay. And here is what the results look like. Okay, a mess. Right. Let's see what's going on here. Okay. So what I'm plotting here is the speed up obtained versus the number of loop iterations, the number of iterations in that loop. Okay, and then a separate line for different numbers of threads. So I've got 2, 4, 8, or 16 threads here. Okay, so what can we see? Well, if our loop is not big enough, then, okay, so remember a speed up of 1 would be equal to the sequential performance. Okay? So for small loops lengths, the speed up is much, much less than 1. It's slow down. And what's happening there is basically death by synchronization. Okay, the barrier at the end of the loop is the overhead of that is completely wiping out any benefits of parallelism. Okay, and I actually need something, in order to break even here, in order to get up to the speed of 1. So depending on the number of threads, but I need somewhere between like 50,000 or 200,000 iterations in the loop, which is maybe surprising. Okay, but that's how much work you need in the loop to overcome the overheads. I mean, that loop gets it gets vectorized, so it's the potential flop rate is very high. So it's very heavily demanding on the bandwidth. But it also kills you. You just get killed by synchronization down here. For 2 threads, well, it pretty much behaves like you could naively expect. Okay, so the speed up eventually reaches 2. Okay, and then stays there. Okay, so once we've overcome the overheads of the parallel region, we end up with a speed up of 2 on 2 threads for any large data size. For 4 threads, okay, so that's this orange line here. Well, we just about make it up to 4, speed up of 4, but then it drops a bit. Okay? And at this, so the data sizes in here were essentially the array fits in the level 3 cache. So we are seeing here the fact that we get just over a speed up of 3 rather than 4 here is because we're saturating we're contending for the bandwidth for the level 3 cache. And then as we get bigger, eventually that array doesn't fit in level 3 cache at all, and then we end up contending for memory bandwidth, and the speed up drops to about a value of 2. And then for 4 threads, okay, we get initial climb and then a bit of wibbling about, and then at some point we get a very big increase. Okay, so what's going on here is that at this point we are taking advantage of the fact, okay, we've now got 8 threads, so we now have double the, we now have twice the, we've got 2 L3 caches. So at some point that array fits into 2 L3 caches, whereas it didn't fit into 1 L3 cache, which one thread had access to. So you get this massive spike in speed up, but it doesn't last. Okay, as we get bigger, then we drop back to about a speed up of about 2 when we're contending for the main memory bandwidth again. Okay, and same for 16 threads. Okay, we end up with there's a peak here because we've now got 4 level 3 caches extra. We get this extra L3 capacity here, which causes this big spike. But you can see that even so, you never get much more than, you get a little bit better on 16 threads than 8, but you never get more than sort of 2 and a bit times speed up, even with 16 threads running. Okay, Laura says, can we read the origin of the peak again here? Okay, yeah, so you remember computing speed up, what we're doing, remember what we're doing is we're comparing the execution time of the parallel loop to the sequential or one thread version. Okay. So for this particular data size here, the array does not fit in one level 3 cache. So that means that the one thread version is basically accessing main memory for this particular size. Once we go to 8 or 16 threads, then we you get it. Okay, we've now got access to 2 level 3 caches or 4 level 3 caches, and so we're so at this point that version is with 8 or 16 threads is running is using the L3 cache instead of main memory. So that's where this spike comes from. So why can't 8 threads achieve why can 8 threads achieve it? Yeah, okay, it's precisely this issue. Okay, you get it's because 8 threads have access to double the amount of level 3 cache. Yeah. Yeah, it only works because you're doing it multiple times. Yeah. Okay. Otherwise, you wouldn't get any. That's correct. Okay. This is only because I'm doing it enough times that the data is actually resident in the cache. Otherwise, otherwise, if you just looked at the first time you executed it, then everything would still be coming from main memory, and you'd see contention for memory bandwidth everywhere. Yeah. So this is only provided repeated enough times that I'm really measuring that the data is cache resident and not all coming from main memory. Yep, spot on. Anyway, you can see that particularly. I mean, this architecture is particularly bad. Okay, in the sense that you can about two threads is enough to saturate the entire memory bandwidth for the full NUMA region, and adding more threads when you're contending for memory bandwidth just gets you very little additional performance. Yeah, that's pretty sad. I mean, you can look at it the other way around and say, okay, well, actually, this is this is a result of one thread being able to access a big chunk of the memory bandwidth. So you can look at it both ways round and say, is this a good hardware design or not? Okay. Well, say it means that if I'm only running one thread, then it gets a lot of the memory bandwidth. But for so for HPC applications, it's where you want to be using all your cores, it is pretty sad. Yeah. And things have not improved. We compare. ARCHER2 compared with, you see a lot on, AMD is quite bad for this. So you compare, so our previous system, so Archer had Intel Ivy Bridge, and the bandwidth per, if you use all the cores, the bandwidth per core of the AMD ROMs is about 75% of what we used to get from Intel Ivy Bridge. So the bandwidth per core has actually decreased between our two systems, which were purchased like 6 years apart or something. Hey ho, it's life. Okay, what else? Yeah, cache space contention. Okay, so if we're sharing level 3 cache, then again, you might not see good scalability because one core is able to access the whole cache. In that case, if you're into the business of implementing cache blocking in your code, then you have to beware of tuning your cache block size, your block sizes for a single thread, and then running multi-thread. And if what you really want to run is multi-threaded code, you'll end up with you potentially end up with the wrong block size. And then hardware threads. Okay, so hyperthreading, simultaneous multi-threading, whatever you like to call it. So then if you have OpenMP threads running on the same core, we'll also contend for they also have to share the floating point units, for example. And so hardware threads, they tend to benefit, it's rare to get much benefit from them. If you do, it tends to be codes where threads are idle because they're waiting on memory references. So codes which are not memory bandwidth bound, which are not floating point bound, but which are memory latency sensitive. And so it tends to be code with non-contiguous or kind of random looking memory access patterns. And that's codes which are bandwidth hungry or which are saturated floating point units typically don't benefit from using hardware threads. And they may actually run slower because you need to, if you're going to use the hardware threads, you actually have to double the number of OpenMP threads or double the number of MPI processes. And that's just going to increase your other parallel overheads. It's going to increase your synchronization costs. It's going to increase your idle time, typically. So it's rarely, the trade-off is rarely worth it. And that's why on a lot of HPC systems, the hyperthreading is disabled is disabled by default. Okay, it's turned off, and you have to request it specially. Ashutosh asking, is there any formula for deciding block size for cache blocking? Not directly. You can, if you know these, if you know the number of arrays that your loop is axing, then you can do some counting of number of bytes. Okay, so you can decide how many you can count how many bytes of data your block of code is going to access, and then try to match that to the usually something that's a little bit less than the size of the cache. But it depends on the code. It depends how many different arrays your loop is accessing. Could be L3. I mean, you could be blocking for L3, but you could also be blocking for L2 or L1. But then this problem of shared caches doesn't hit you then. So yeah. But if you're blocking for L3, then you would need to be you need to be aware of the fact that you've potentially got multiple threads sharing that L3 cache capacity. So the other way you can, obviously the other way you can contend for hardware resources is by oversubscribing them. So this is why running more threads than you have hardware execution units is generally a bad idea. Because what's going to happen is the operating system is going to try to give each thread a fair share, and then you run all sorts of problems. The cost of stopping, doing the context switch, the cost of stopping one thread and starting another is quite high. So thousands of tens of thousands of clock cycles, and it also means that your threads typically start migrating about, and ruins all your data locality as well. So this is very rarely a good idea to run more threads than you have cores. Okay. So that's the 6 main things. And the last one, the last half is compiler non-optimization. Thankfully, this is a very rare occurrence, but it can happen, and it's just good to be aware of the possibility. So what happens is, in rare cases, adding OpenMP directives can inhibit the compiler from performing its normal sequential optimizations. And the symptom that you will see here is if you run your parallel OpenMP code on one thread, then it might have a longer execution time than the sequential code compiled without OpenMP. I say, thankfully rare, but if it does happen, it's a pain because it can be really difficult to find a workaround and figure out something that's going on here. Sometimes you can cure stuff by if you have the choice between shared or private, then sometimes privatizing things can help, or making local copies of making a local copy of a variable that's passed through an argument list so that the compiler can better determine its scope and access patterns. So things like that might help, but it can be very difficult to figure out. I saw one a while ago in a Fortran code where it had a slightly strange idiom. So it was passing arrays into subroutines, and so in Fortran you can just pass it's all passed by reference, but if you can either just pass the name of the array, or equivalently you can pass the first element of the array. Okay, so it's the same thing because it's all passed by address. So this code was doing the unusual one, which was passing the first element of a multi-dimensional array instead of just the name of the array, and for some reason that caused this sort of problem. So just compiling with OpenMP and running on one thread took about twice as long. It's just about double the execution time compared with the sequential code. But so just be aware that it might, if you're unlucky, it might happen to you one day. But yeah, and that's maybe what's going on. Okay, so yeah, what can we do about this? Okay, so you might be in the situation. Okay, so your code's giving you poor speed up and you don't know why. So what do we do? Okay, well, hopefully we don't do the first thing. Okay, don't just give up. So what can we do? I think the approach that I like to think about is to try and classify and localize the sources of overhead. Okay? And try to figure out what type of problem is it. Okay, so which one of those 6 things, or which one of those 6 sources of overhead is causing me the problem? Okay, it could be more than one, and whereabouts in the code is it happening? Okay? So if I can work that out, then I have a fighting chance of being able to fix it. If I can't work that out, then I'm basically just shooting in the dark. So yeah, you can use some tools to help you. So you can get a lot out of just using timers, but also hardware counters and profiling tools are also beneficial here. And if you're going to be using a particular system on a regular basis, it's profiling tools. These tools take some effort to get to learn how to use them. But if you're doing regular development on a particular system, then it's worth learning them. Yeah, and then fix the problems which are responsible for the large overheads first. Okay, so if you can not only classify and localize it, but also quantify it. Okay, so you figure out which are the really bad problems and which are the minor problems, and concentrate on the big problems. Yeah, so profilers. So for OpenMP code, standard profilers can be pretty confusing because typically what they do, what they report is they accumulate the time spent in functions across all the threads. They don't give you per thread information, and they don't necessarily tell you the spread of value. They just give you basically an accumulated time, and they don't tell you that whether some threads are spending more or less time in a particular piece of code. You know, you can do a lot with timers. So particularly, you know, if you add timers around every parallel region and round the whole code, then you can at least work out which regions are giving you the worst speed up, and basically don't assume that the time spent outside parallel regions is necessarily independent of the number of threads. Okay, so you can, if you have the time around the whole code and you time every parallel region, then you can, by subtraction, work out how much sequential time you've got. Yeah, vtune's pretty good. Okay, so there's a bunch of tools which are useful here. So yeah, Vampire, vtune, Tau, ARM map, Craypat for craze. I'm quite a fan of, again, it's a bit of an individual choice here, and depends what you've got available. I like Scholastica as a tool. Has the advantage of being free. If you care about these things, so if it's not on your system, and you're prepared to install it yourself, you probably can, because it does do this. It does at least try to do this process of breaking down the overheads into different categories. It does a good job of instrumenting the OpenMP runtime and reporting where your time is being spent. It'll tell you how much time you're spending in a barrier, and it'll distinguish the actual barrier synchronization time from it'll tell you the idle time. It also tells you, which some other tools don't, it'll tell you how much time threads are spending idle between parallel regions, and so on and so on. Yeah. Problem with most of these tools is that they don't tell you anything about the communication, or tell you very little about the communication or hardware resource contention. So like bandwidth contention. They're just not very good at picking that stuff up. One tool that is quite interesting is Thread Spotter, okay, because that does something different. It's not a traditional profiler. It's basically doing statistical sampling of memory accesses and then replaying that through a cache. Yeah, Intel Advisor for bandwidth. Yeah, it'll tell you something. Yeah. It might tell you what bandwidth, what your achieved bandwidth is. So that you might get something out of that. Again, it's a bit hard. Yeah. If you're not on Intel processors, though, you're out of luck, I guess. Depends what hardware, what's available in the hardware for measuring bandwidth. Okay, good. Fine. That's me gone on rather a lot. Next 3/4 of an hour or so, at least, Queven and I will be around. So if you've had enough for today, that's absolutely fine. If you want to carry on doing some of the practical exercises, we'll be around for another 45 minutes or so, and for any help that you need. So please feel free in this course just to do whatever exercises you feel like, or whatever interests you. Don't feel that you have to work through them all in order. Just do what suits you. Absolutely. Okay. Hope that was useful. So we'll be around for until 5 o'clock UK time. But if you want to head off, then please do, and hopefully we'll see you tomorrow. Yeah, Lorenzo.
I'm still like shocked about that graph that you show on the AMD thing. Because
Yeah.
out of curiosity, when you show this to the AMD reps, what did they say?
I haven't showed it to them, but I don't think it would come as any surprise.
Okay, no, because when you talk to them, it's all like it's great and it's incredible, and and we've been
Sure.
trialing a lot of their system, and what we see is that linear scaling is pretty much like a unicorn, and we have to use those machines as mini server themselves. So just like use very small amount of lots of team of threads, small cores to achieve decent scalability, for the reason that you showed here. So, and I don't know if that's the design they have in mind. So they think about this I-core count machine as like sort of like new generation servers where they want to spin like multiple applications that are not particularly compute hungry. I don't know.
I mean, so the AMD, they've clearly gone for maximizing the number of cores.
Yeah.
Right. So they put a lot of cores on the chip, but that's meant some compromises. Okay. So the amount of bandwidth per core that you get is not that great. Okay. And you have this contention problem. I say you can look at it two ways. I mean, you can say, okay, so yeah, you get, one core can get half the bandwidth out of a NUMA region, and that's not true on other hardware necessarily. Okay, you don't get so much bandwidth for. They've done some work to make sure that a single single core can access a lot of the band, most of the band or half of the bandwidth. And then there's also this complexity with you've got lots of NUMA regions, and then you have these L3 caches which are split across 4 cores, so you have this quite complicated hierarchy. It's quite a messy hardware design.
Yeah, I mean, so far what I've seen is that the best configuration is where we bind affinity to the L3 cache, so we force the cores to work on that same L3 cache, and that's the one that seems to perform. I think it follows exactly this trend, so it just works a bit better than than other configuration, but not particularly like mind blowing.
Yep. So we've done quite a lot of work looking at hybrid codes, hybrid MPI plus OpenMP codes. It's for sure never worth going more than 16 threads per process, because then you're going outside a NUMA region, and that's usually just disaster. So it's usually like 4 threads per process, maybe 8 sometimes, maybe 2 sometimes is usually the best option. Yeah. It depends a bit on your application as to how sensitive you are to L3 cache usage.
Thanks so much. This was really, really eye-opening.
Good. Well, thank you for your patience today. I'll hope to see you tomorrow. Okay, thank you very much, everyone. We'll wrap that up there now for today, and hope to see you tomorrow.